Hi guys, so today's video is to tie up any loose ends that you might encounter with the topic stoichiometry. This is simply a continuation of what you learned from last meeting. If you haven't watched those videos, I encourage that you watch them first before moving on to watching this video. Today's lecture is taken from handout L13 from your lecture manual, and we will begin with page 3. Okay, so stoichiometry, the stoichio there is from a Latin origin meaning amounts, and metry means measure. So stoichiometry is measuring the amounts of the substances that are found in the reaction. As you know by now, you're going to need the stoichiometric coefficient from the balance equation in order to draw a relationship between substances that is found in the reaction. What that means is that if you're given the amount of the reactant, you'll be able to determine the amount of the product formed and vice versa. If you're given the amount of the product, you will be able to know how much the reactant you will need in order for the reaction to proceed. So I'm going to try to use the third problem as an example here. All right. So this is a combustion problem. You have this fuel C2H6, and you're going to need oxygen to help burn the fuel. It will form into carbon dioxide and water. So the question states how many moles of oxygen are required in order to burn 2.4 moles of the fuel. So you have the amount of fuel in moles, that's 2.4 moles. And you're asked to find the amount of oxygen needed to burn the fuel. Here, we're going to use the stoichiometric coefficient of what is given and what is asked for. Notice that there are several stoichiometric coefficients found, but we're only going to focus on what is given and what you are asked for in the problem. So to solve this problem, let's set up the dimensional analysis. How many moles of oxygen is needed in order to burn 2.4 moles of the fuel? And then using the molar ratio or the stoichiometric coefficients, for every 2 moles of the fuel, you're going to need 7 moles of the oxygen to burn it. This gives you a number of 8.40 moles of oxygen. So technically, you'll be able to calculate for the amounts of carbon dioxide and water produced from this reaction. All you need to do is use the stoichiometric coefficient for that of CO2 and water. Okay. So if we have the concept map, all right, or that is, let's solve for the carbon dioxide. So how many carbon dioxide is needed or produced if you're going to burn 2.4 moles of a C2H6? We have for every 2 moles of the fuel, you're going to produce 4 moles of the carbon dioxide. Notice I'm going to use this one for CO2. Okay, so I have double the amount so that I have 4.80 moles of CO2 produced in this process. Remember though that sometimes you will be asked to find the amount of substances other than moles. So basically you could be asked to find the amount of the reactant oxygen in grams, or the amount of oxygen, how many molecules are present in a 8.4 mole sample. Okay, so you're going to need your knowledge in chapter 6 and how to convert mass to moles, or how to convert molecules to moles. So remember the concept map, we have it written in a horizontal formation. So we have molecules to moles to mass and vice versa. If you're given molecules, to convert it to moles, you're going to use the Avogadro's number. Or if you're given the mass and you're asked to solve for the moles, you're going to use the molar mass, because that's the one that has the unit grams per mole. Now we write that out as a horizontal formation, but technically now I can rearrange that into a vertical formation. So this concept map right here, just rearrange that so that it becomes a vertical formation. And so if you have information other than moles, you can easily convert mass to moles using the molar mass. Or if you have the information of the reactant as molecules, you can convert that to moles using the Avogadro's number. Once that it is in moles, you can easily calculate for the amount of the product by using the stoichiometric coefficient. Okay, so imagine this balanced equation with a mole pedestrian crossing. You can't cross this reaction not unless you're a mole. So once you're a mole, then you can use the balance equation. Now, if you're asked to convert it to its equivalent mass, you can do that by using the molar mass of the product, or if you're asked to figure out how many molecules are present, then use the Avogadro's number. So say for instance, you're given this combination reaction of hydrogen and oxygen to form water. You can interpret it in a number of ways. You can look at it through the molecular point of view, wherein you have two molecules reacting with one molecule of oxygen to produce two molecules of water. Or you could look at it in a bigger batch. So for every 2 moles of hydrogen, you will need 1 mole of oxygen to produce 2 moles of water. You could also look at it in terms of the mass component or the mass point of view. So know that the molar mass of one hydrogen is basically 2 grams per mole. And so if you need 2 moles for this reaction, then that would total up to 4 grams of hydrogen that will be needed in order to react with 32 grams of oxygen to form 36 grams of water, and that's 2 times 2 moles produced, wherein each mole weighs 18 grams. Okay, so that's 36 grams of water. Okay, so let me move on to the next problem or next page, wherein it's pretty much similar to the problem on page 3. You still have 2.4 moles of the fuel C2H6. This time around, you're asked to find the amount of oxygen needed to burn that fuel, but instead of moles, you're asked to find it using its equivalent mass. So we started it off in the previous page. You have for every 2 moles of the fuel, you're going to need 7 moles of oxygen. But we have an extra step here since we're not asked to find the amount of oxygen in moles, but rather how much weight do you need. So convert that to mass by using the molar mass of oxygen. The molar mass of oxygen is 32 grams per mole. That means for every mole of oxygen, it will weigh 32 grams. And by doing this extra step, we have converted the amount of oxygen in terms of grams. So I have here 268.8 moles of oxygen. So again, you're only going to use the balance equation to be able to bridge one information to another. You're going to use the stoichiometric coefficient or use the mole ratio. And if you're asked to convert or asked to find the mass of that product in terms of, if you're asked to find the mass of that product, all you need to do is use the molar mass in order to convert moles to grams. Or if you're asked to find the molecules, you're going to use the Avogadro's number. Okay, and same thing holds true if the information of the reactant is other than moles. You could use molar mass. Say if it's given in grams, use molar mass to convert it to moles. Or if you're given molecules of the fuel, then use the Avogadro's number to convert it to moles.